All right, today we are diving into a total powerhouse of an algorithm, one that you absolutely have to have in your programming toolkit, Depth First Search, or DFS. Stick around, because by the end of this, you'll get exactly how it works and, more importantly, how you can use it to ace those coding interviews. But hey, before we get all technical, let's start with something you can picture. Imagine you're standing at the entrance of a massive, super complex maze. How do you find the way out? Seriously, take a second. What's your strategy? Chances are your gut instinct would be to just pick a path and go for it. You'd follow that one corridor as deep as you possibly can. And when you hit a dead end, what's the move? You turn around, you backtrack to the last intersection where you had a choice, and you try a different path, right? You just keep doing that, exploring one full route to its very end before you even think about trying another one. Well, guess what? Congratulations! You've just used your intuition to figure out the core logic of this entire algorithm. That exact strategy, going deep down one path before you backtrack, that is precisely what we call depth first search. So let's make it official. Okay, let's take that gut feeling for solving a maze and translate it into the language of computer science. It's the exact same idea, really. We're just swapping out corridors and intersections for things called nodes and edges inside a data structure called a graph. So here it is, the textbook definition. DFS is an algorithm that explores as far as possible along each branch before backtracking. See those keywords, as far as possible and backtracking? That's our maze strategy right there. Go deep first and only retrace your steps when you absolutely have to. And this isn't just some abstract concept we came up with. Nope, this was formally analyzed way back in 1972 by computer scientist Robert Tarshan. He showed that this simple idea could be the foundation for some incredibly efficient, what we call linear time, algorithms. It's a true classic. So how does a computer actually pull this off? Let's peel back the layers and look at the step-by-step process. This is how it all works under the hood. The whole process is super methodical. First, you pick a starting point, a node. Now the next step is absolutely crucial. You immediately mark that node as visited. Then, you look at its neighbors, pick one you haven't been to yet, and just dive down that path. If you land on a node and all of its neighbors have already been visited, well, that's a dead end. That's your signal to backtrack to the previous node and see if it has any other doors you haven't opened yet. You just keep this rhythm up until every single node you can reach has been visited. Okay, I really want you to pay attention to this slide, because this is the single most important detail and the #1 place people trip up, the visited list. Without it, if your graph has a cycle, a path that loops back on itself, your algorithm will get trapped forever. It's an infinite loop, just going back and forth between the same nodes. But by marking nodes as visited, the moment our algorithm sees a node it's already been to, it knows, nope, not going that way again. It's such a simple idea, but it's what makes the whole thing work. Now, in computer science, it's never enough for an algorithm to just work. It also has to be fast. It has to be efficient. So let's talk about performance, or what's known as time complexity. This is a huge topic, and something you'll definitely be asked about in a technical interview. The time complexity for DFS is written as O of V plus E. Now, don't let the notation scare you. It's actually pretty simple. V just stands for vertices. Those are the points or nodes in our graph. And E stands for edges, the lines connecting them. All this formula means is that the algorithm's runtime grows in a straight line with the size of the graph. It basically has to touch each node and travel along each edge just one time. And that, my friends, is incredibly efficient. It's what we call linear time performance. But, and this is a big but, there is a catch. To get that amazing O of V plus C speed, how you store your graph really, really matters. The key is using something called an adjacency list. This just gives each node a simple list of its direct neighbors. The alternative, an adjacency matrix, is this huge grid that forces the algorithm to check every possible connection for every single node, even if the connection doesn't exist. This slows things down a lot, all the way to O of V squared. So yeah, that's why adjacency lists are the undisputed champ for DFS. Now, DFS isn't an only child. It has a very famous sibling called breadth first search, or BFS. So to really understand DFS, we need to put our Deep Explorer up against the Wide Explorer, BFS, and see when you'd pick one over the other. The huge difference between them is all about their search pattern. DFS, as we know, dives deep. It's like a cave explorer going all the way down one tunnel before coming back. BFS, on the other hand, explores wide. It checks all the immediate neighbors first, then their neighbors, and so on. spreading out level by level, kind of like ripples in a pond. This makes BFS perfect for one very specific job, finding the absolute shortest path between 2 points. So, they're just different tools for different jobs. Okay, let's bring it all home. When are you actually going to pull this tool out of your toolbox in a real-world coding challenge or a technical interview? Knowing the right time to use DFS is your secret weapon. And man, is it versatile. You can use DFS for something as simple as checking if a path even exists between 2 points. It's amazing at detecting those cycles we talked about, that infinite loop problem. It's also the backbone of something called topological sorting, which sounds complicated, but is just about figuring out dependencies, like the right order to take your classes to graduate. And, of course, it's the perfect match for any puzzle that needs backtracking, from solving a maze to cracking a Sudoku. So there you have it, depth-first search demystified. We've gone from a simple maze strategy all the way to a powerful problem-solving tool. You get how it dives deep, how it backtracks, and you know where its real strengths are. So now that you know the path, it's time to put it to the test. Here's a classic interview problem for you. Can you use DFS to find and count all the separate islands? Give it a shot.